by our collaborators from KAIST University in South Korea, represented by Sang-Guk Jang and Dr. Jang. And from our side, from University of South Florida, it's my advisor, Dr. Kwon and Dr. Shah, and myself. So here's a quick outline of today's presentation. So first I'm going to introduce the problem, discuss how we formulated as a reinforcement learning problem, present some of our computational methods that we have developed. Here we are going to talk about some methods that we have tried and succeeded, and some methods that we have tried, spent some time, but actually failed. I think it's also important to discuss about them. Then we are going to have some numerical analysis and ended up with some lessons learned. So the topic of this presentation is about free floating electrical vehicle sharing systems. So as the name suggests, it's about sharing the electrical vehicles among customers, and there's an operating company which provides these EVs. So from customer viewpoint, how it works is as follows. You just need to download the app, reserve the EV, go there and drive the EV, park wherever you want, and just go. So these programs usually do not require customers to pick up or drop off the EV in a certain locations, and it does not require them to charge them. So that's why it's called the free floating. So let's look at some examples. So it's a car to go. I think here it's in Amsterdam, but it used to work in United States as well. It does not work anymore. WeShare still operates in Berlin. And there's a similar program offered by Blue LA in Los Angeles, but it's a little bit different because they require customers actually to charge and park in certain locations. As you can see in the map, you can see the availability of AVs, the conditions, the locations, all that information is available. But the topic of today's discussion is going to be about the services offered by Car2Go and WeShare when customers are not required at all to charge or drop off in a certain location. So it's like real free floating system. So for these programs actually to be successful, there's very important problem called rebalancing. So why do we need to rebalance the network? Imagine the busy days, the customers have used EVs, and certainly they're going to relocate EVs from one location to another. And we are going to have a system, and in some zones there's a lot of EVs, and in some zones there's like lack of EVs. So based on the predicted demand for the next day, what we need to do, we need to relocate EVs from certain zones and charge them, and then relocate back to demand nodes. So this problem is called the rebalancing, and we are going to talk about the static network. What do I mean by static network is that we are not going to have any we are going to basically have a negligible demand from customer side, and the main influencer in this system is going to be the operating company, which is going to perform this relocation of EVs. By the way, if you have any questions, just feel free to stop me and ask questions. So this problem, how it's solved in existing programs, is actually very simple. Like around 12 a.m. in the morning, the shuttle of the drivers actually going to route around the network where the drivers are going to be picked up and drop off, and these drivers are going to actually relocate EVs, either if it needs to be charged to a charging station and then to demander nodes, or directly from supply nodes to demander nodes. So let's look at the sample network that we can actually have. As you can see, there's a lot of nodes, different color representing demander, supplier, charger, depot. So what's the purpose of the shuttle? So in this case, the depot is where the shuttle starts its journey, and it starts to rotating around by dropping off drivers or picking up drivers. So at the end of the day, we need to have the case when all of these red nodes should disappear, meaning that they have EVs with sufficient charging levels that are ready to be served for tomorrow. And all the drivers who relocated these EVs are picked up, sit in the shuttle, and come back, return back to the depot. So that's the whole purpose of this journey. So actually, it seems to be like quite straightforward, but there are two problems we need to solve. First problem is how to efficiently rotate the shuttle. And the second problem is where to relocate the EV. So I will straightforwardly mention that our purpose of this project is only about routing the shuttle. We are using the EVs relocation based on the role-based approach, meaning that EVs are going to relocate it either to closest charger nodes, available demander nodes. So we are not solving that problem. We are only concerned about the shuttle routing problem. However, the shuttle routing problem actually has a heavy influence both on the EV relocation problem and in itself. For instance, imagine that we have dropped off the driver here. So dropping off the driver here is going to influence where this EV is going to end up to. Is it to this red node or to this red node? So because in this case, it's going to end up here because we are saying that we are going to drop off to the closest available demander node, right? So it also means that our EV then must visit this node to pick up the driver. So our first initial decisions are going to influence our subsequent decisions. So there's a highly interdependence here. So now let's think how we can actually solve this problem. If you have a shuttle and we have 3 drivers in shuttle, one of the ways actually to solve it, actually get rid of all the drivers first by dropping off each of them at these supply nodes and then start to collect them back. Or we can do it different way. We can first drop our drivers and pick them up. So there's a lot of mixing strategies that we can deploy as well. So in the next slide, I'm going to show that actually there's so many opportunities to explore to come up with good solutions, that keeping track of these possible solutions is actually one of the main challenges. So for instance, imagine the case when we have 2 suppliers and 2 charger nodes, and we need to somehow route the shuttle. Are we going to have a case when we are going to assign each EV to a charging station, or we are going to make sure that in our solutions, we are allowing reusing the shuttle again as a charging station again and again? And another main trade-off in this problem is actually the waiting time versus the traveling time. So imagine the case when you have EV, which does not need to be charged, but are located farther away compared to the other supplier node. And which one do we pick? Are we going to charge and then relocate? Or are we going to directly go to the farthest away supplier node and bring that EV and then pick up the driver? So there are so many things to consider, and this network is going to have many nodes, many different conditions. So keeping track of all of these possibilities is not easy, especially with human-driven solutions, which is deterministic heuristics that we usually deploy, right? We usually to simplify our solutions, we stick to some certain rules and we keep exploiting that idea. For instance, in the existing solutions for this problem, they assume that the supplier nodes are assigned to charging stations, so they completely ignore the possibility of reusing the charging stations. And it is, of course, is going to result in a huge opportunity lost in terms of solutions, but at least with this solution, we can exploit it and develop some human-driven solutions that are understandable and actually explorable for us. But at the same time, we have neural networks which have this capacity is to see some patterns in the networks, in transportation networks, and learn from them and explore all these possible solutions in a systematic way, and somehow learn it so its generalizable solutions are derived that we can apply to other networks. So with this opportunity, we decided to start this project and we tried to solve this problem. So let's a little bit discuss what is actually reinforcement learning. So if somebody asks me what's reinforcement learning, I always reply that it's a self-teaching system. So why I do say that, there's 2 reasons. First of all, in all machine learning, other areas of machine learning, the first thing that you need is the data. And here, the beauty of RL, you don't need the data, you need a simulator. So if you have the simulator and the agent, you can just basically let them interact with each other. Basically, agents interacting with the environment or simulator, and they're generating the data. So it's self-sufficient, it has its own data, and it's going to receive data in terms of rewards, the states it has produced, and try to learn so that as to maximize the total expected reward. So it's trying to learn based on the system. So, however, this is not just random like process going on in this system. It's all of this is governed by Markov decision process. And as we know, in Markov decision process, there's two conditions pretty important. First is that we need to have a Markov property, and second, that this agent, the simulator agent, is the only influencer. So that environment basically is influenced by the only agent, not any other forces. So with all this in mind, we formulated the Markov decision process for single shuttle routing problem as follows. So let's first look for the Markovian property. Do we have it? Here, let's imagine that we are in some node and we need to pick the next node to visit. So for that case, the most important thing to decide that decision is where I am located right now. It does not matter what I have visited before. What matters is at which node right now I am to pick the next station to go. So with this, we have formulated the state space as a network, which consists from nodes. And for each node, we define its location, XY coordinates, number of EVs, a number of drivers, charging levels, and the expected transitions if it's coming or not. And for action set, of course, is going to be the index of the nodes that we're going to visit next. Reward function, we decided to go with the total time spent in the system. Why? So just looking at the total distance traveled is not going to be the case for this situation, because we have a charging stations, and in charging station we need to wait. So there's a waiting time as well involved. That's why we need to calculate the total time spent in the system. So in that case, our aim is to minimize the total time spent in the system. So we want to fulfill all the requirements, all the relocations, and do it as fast as possible. So it was a single shuttle case. But how about if you have multiple shuttles? How we are going to formulate it as Markov decision process? So this idea works with if we have a central controller. So as I mentioned before, for MDP to work, we need to have non-stationary environment, meaning that only a single agent is influencing the environment. And if you have like several shuttles, and we believe that the central controller is basically controlling all of them, we still are under a single shuttle MDP. So with this idea in mind, we are going to have a central control, which is an agent, and it sees all network. So, but the action space of this controller is going to be pretty large, because it's going to control not only a single shuttle, in this case, it's going to control several shuttles. So it's a joint action space, and it's going to receive only a single reward, which is a total time spent in the system, and like all the shuttles leave the depot, and when all the shuttles will be returned back with all the drivers in it. And our aim is to learn directly the policy. We're not learning the value function or Q-value function. We are directly learning the policy. And in this case, it just turns out to be that the value function is going to estimate the total time spent in the system. So this is a just graphical view of our framework again, to make it more clear. So as you can see in the left side, in a single shuttle case, we have an agent, and basically that agent is in only the single player who is influencing that whole network, and agent is a shuttle. In our central controller framework, we are going to have multiple shuttles. Of course, all of them going to influence the network. However, all of that shuttle's decisions, routing decisions, are done by a single controller. So still we can think that there is a single agent playing out in the system, and that only agent is influencing it. So actually, I need to talk here about multiple agent reinforcement learning that we spent quite a long time trying to work with. So when we started this project, actually we started with this formulation. So we decided that each shuttle is going to be independent, autonomous agent, and it's going to, in that case, non-stationary assumption will be gone, and all of these agents are going to influence the environment. And to mitigate the situation, we need to use a partial observability. So the problem will be formulated as PMDP. So what do I mean by that? So here, each agent, each shuttle is the agent, but it does not see the whole network. It only sees, for instance, the area under this circle, and meaning that only this shuttle is going to have this area, so stationary assumption sort of holds. And then in this case, we are only limited to visit the nodes under this circle. Of course, it's going to put a lot of limitations on our routing policy because we are limited in our action space. And actually, we tried hard to make it work, but turns out this framework did not generate the competitive results. So that's why we had to go with that idea of central controller. However, there is some beauty of this method as well. For instance, it's going to have each shuttle is going to be independent, autonomous agent. So there is no need for central controller. Second, since there is a sort of network is partitioned to small spaces, the joint action is going to be easier to explore. So we are going to have, we are most likely going to have less scalability issues in this case. However, still because of the spatial observability, it does not produce so much competitive results. I believe this framework may be more suitable for dynamic environment. So now let's talk about how we actually solve the problem. When we immediately said that in this problem, we are going to directly learn the policy. So we are not interested in learning the value function and key-value, but we are going to learn directly the policy. So what do I mean by policy? The policy assigns the probabilities to each node to visit. And most likely we are going to go to the node which has the highest probability, right? So here's a very famous A to C algorithm, very well known for learning the policy gradients. So it consists from two networks, actor and critic. The goal of the actor is to figure out the policy. So what does it do? It interacts, the actor receives the action taken so far as the state it has ended up with, and it all stores all that history in its memory. And out of that, it needs to produce some policy. Critic, on the other hand, is only concerned about giving a feedback to the actor by estimating, approximating the value, the total time it expects to spend in this given network, but by only taking the initial state. So based on this information, advantage function is calculated, which is basically the actual empirical value of R reward, the total time spent in the system, and the predicted approximated value, their difference, to update the critic network. Similar way, we are updating the actor network, but we also have a log of probabilities here. So this is pretty well-known algorithm. We are going with a straightforward way. However, we tried to do something a little bit different. As you can see here, we are using the total reward for the whole episode, which is called the Monte Carlo methods. As you know, in Monte Carlo methods, we need to play out the whole episode, see the empirical return, and then from that update our neural network parameters. So this method is good because it's unbiased estimator. It has a high variance, but still it's unbiased. But there is a temporal difference methods that we have tried actually too. We spent a lot of time trying to train our methods, neural network this way. The temporal difference method tries to learn not only from the whole episode, but from each time step. So it somehow smartly combines rewards received from different time steps, and then tries to learn the value based on this temporal difference error. However, for our problem, this method did not work. And I believe it's because of the structure of the reward that we have in the problem. So if you think this reward in our problem is influenced by two factors. First is the traveling time, and which is basically fully dependent on the distance. And the second thing that is influencing our reward is the waiting time. And this one is actually influenced by the initial charging level of the EVs. And if you only look at one step ahead, a couple of steps ahead, it's still very hard to adjust to learn the reward function that way. So when you play out the whole episode and you actually see the total spend time in the system, somehow it worked out better for us. So this is the actual neural network architecture we have used. It's not new. This is actually very well-known sequence-to-sequence architecture. But first, for VRP problems, it was used by Nazari, very highly recommended paper. So we are using the same idea. I have to say that we explored, before coming to this architecture, we spent quite a lot of time trying different, like, feed-forward networks with some combination of RNN, Aigerim, a lot of different architectures. But at the end of the day, there is something that is very suitable to our problem about the current presented architecture. So if you look at the general view of the architecture, it consists from like encoder, or we call it embedding. Basically, we are taking some graph representation, like its dynamic elements, its static elements, passing through the one-dimensional convolutional layer, which is going to basically represent a graph in the higher dimension. And we are only selecting the current selected node and passing only that information to RNN. We are not passing the whole graph to RNN. And then RNN is going to basically store the history of sequence for our routings that we have built so far. And then all of this information is passed to attention. And then attention is going to basically produce the probabilities that we are going to assign to each node. So as I've mentioned before, this architecture comes from the sequence-to-sequence models, which comes from machine translation. So in the sequence-to-sequence models, what's important is that the input to the model is a sequence. In our case, it's a graph. You can think of it as a sequence of nodes. And we also want to get another sequence, which is a route of the shuttle, which is another sequence of the nodes. And it's going to have three parts. Mostly it's encoder, decoder, and attention. And each of them plays a significant role. So encoder, especially encoder, I've tried just to pass that graph representation without embedding encoding. It always produces some inferior results. It's because the neural networks somehow learn better in a higher dimension. So the goal of the encoder basically represents that graph in a higher dimension. And then the decoder, in our case RNN, is just going to take only the selected node. We also tried to pass a whole graph to this decoder. We tried different ways, but passing only the selected node, basically letting it store only the sequence that we have built so far, is also important. And the attention is going to somehow pick up the most relevant information to produce the policy. So that was the sequence-to-sequence models, and let's look what it has yielded to our problem. So first, to mention how we generated the data. We generated the data randomly using uniform distributions, both for XY coordinates, types of the nodes, charging levels, and all that information. And we also need to say that for charging levels, we discretized it, like if there's up to from 0 to 100. We divided into bins like of 5, like 20% each, and so we are going to have a fully discrete space. And we also have 2 benchmarks for our problem. So this a little bit about this benchmark. This benchmark came out very recently. They are pretty competitive. They are based on the deterministic heuristics, like 2 exchange-based netted, that kind of like sort of standard heuristic deterministic methods, and they have 2 solutions that they have developed. First one is a sequential model. In sequential models, they are solving first the EV relocation problem, and then based on the shuttle routing problem. In the second one, simultaneous solutions, they are solving both problems at the same time. So we decided to compare our results with this benchmark. Here, you can see some hyperparameter values that we have used for training. A little bit about training itself. Here's the training graphs for 50 nodes for single and multi-shuttle case. And we have to say that for training, it really depends training time on what input do you provide to the neural network. And it took some time to figure out what features of the graph actually to pass to neural network to train it efficiently. And in general, for this case, I believe with the 20 CPUs, it took around 6 hours to train for 50 nodes. But training time, of course, is going to depend on the training size, first of all, the neural network size. But there are also another important factor that is going to affect it, which is the instance difficulty. So this is a table which generates basically our final results. So we created for each network size, we created like 3 types of the problems, which I prefer to refer as easy, medium, and hard difficulty. So easy case is when you have abundance of charging stations and you can decide which charging station to go. And the medium case is like you have exactly charging stations equal to the exactly EVs that needs to be charged. So you need to actually assign to each of them. And in the last case, when we have like the small amount of charging stations and much more EVs to charge, meaning that we need to reuse charging stations, results are as follows. So the last class of the problems is not solvable by existing heuristic method. So RL can still produce results for multi-shuttle and single shuttle cases. And for the rest of the cases, when you have like still solvable solution by the heuristic, still the solution produced by RL is competitive and even better. So especially with the larger networks and the difficulty of the problem, whereas RL solutions are pretty competitive. So that was actually about the result. What about the solution time? So with the existing heuristic methods, one problem is their like intolerance to the change in the input. So when you change something in the input file, you need to start solving the problem from scratch with the deterministic heuristic methods, because something changed, you need to resolve it. But RL, on the other hand, has this ability, if it's trained, if we are talking already about trained model, so you saved it, so wherever you pass, it's going to generate the solution in a fraction of a second, because as long as you maintain that uniform distribution that it has been trained on and some basic network structure. So as you can see here again, the network size increases. This is for one instance out of 128 instances taken as average. So as you can see, the heuristic solution really is going to get longer as we need to increase the network size. But RL, if it's trained, it's going to be done in a fraction of a second. So now let's look what we have generated actually, what's our policy. So this is exactly the same network that we have showed at the beginning of the presentation, if you remember. We are in the single shuttle case, we have 3 drivers here, and we started our journey from the depot. So these numbers here represent the order of the visiting the node. So first I visited this node, that's why its link number is 1. Second, I visited this node, this link number is 2, and keep going. So blue ones are the supplier nodes, meaning that we have visited first 3 all suppliers. We get rid of all the drivers first, and then we are going to pick up one driver, go to one, drop it off, and then pick him up, drop it off, and keep going. So we are going to do it until we visited all the red nodes here, the demand nodes, all of the is satisfied, requirements is satisfied. But I also want to mention one thing. There's two things that we can observe. First, in this case, when we are visiting this first supplier node, we dropped off the driver and he took the EV to this charging station. As you can see, notice this charging station is not visited by the shuttle at all, because it allowed the EV and to driver to wait until EV is charged, and then when the charging is done, the driver is directly taking it to the demand node, and then only shuttle is picking it up. This kind of solution is currently not available in existing heuristic solutions. At the same time, the same RL allows us, for instance, if this EV is taken by driver to this charging station, and actually shuttle is immediately picking up that driver and continuing its journey. So it allows both these cases when the driver is waiting with the EV to charge, or driver is picked up and the EV is charging on his own. Now let's look at the multi-shuttle case, which I think is even more interesting. In this case, we have 2 shuttles and again 3 drivers in each. So we are again starting from the depot, and the one shuttle is going to visit in a pink colors here, first 1, 2, 3. It's again immediately visiting 3 supplier nodes. Similarly, the second shuttle is again visiting the supplier nodes first. But one interesting thing happens here actually. If you notice, this this driver is dropped off by the first shuttle, and it's relocating this EV from this node to this charging station, but later it's picked up by the second shuttle, which is represented by red. So this kind of being able to pick up by different shuttles is also not available in the existing heuristic solutions, because how they solve this multi-shuttle case is actually, they don't solve the whole network. They somehow cluster the network into some k number of shuttles, and each shuttle is basically routing in that sub-network and fully autonomously, like doing its routing decision on that small network and then returning back to the depot. While in our solution, we are not splitting the network at all. We don't need to worry about clustering, but we are just generating immediately the solutions. And I also have to say that it's not always possible to well cluster the nodes, cluster the network, or sometimes it's even not impossible to split the network based on the number of shuttles. So again, we can see some flexibility in these RL solutions. So last, let's also talk about our lessons learned from this research. Probably the number one thing that I learned from this research is that simulation is really important. I didn't mention how we built the simulation here, but we can discuss later. But simulation needs to be flexible, it needs to be run fast, and of course debugging should be easy as well. So also it's going to have some masking scheme that I didn't mention before, that is going to help us to maintain the feasibility of solutions. Second, if you are solving the problem over the graphs, probably if you don't deploy any graph embedding or graph encoding, some representing that graph in higher dimension, learning from it is going to be very challenging. So from our experience. And the third thing, we have tried our Monte Carlo method, we have tried temporal difference method, but at the end of the day, for our problem, Monte Carlo method worked, and we believe it's because different reward function structure here, which is basically influenced by waiting time and traveling time. So if you don't calculate the computer total time spent in the system, learning based on a single step was a little bit challenging as well. Okay, that was it about my presentation. If you have questions, please let me know.
Any questions for Aigerim?
I can ask a question if no one has a question.
Go ahead.
Okay, so what do you mean when you say Monte Carlo methods as opposed to temporal difference methods? Are both of these reinforcement learning methods, or
yeah.
is okay? All right. Okay, and the other question I had is, you said the RL algorithm, it takes like a very short amount of time to run. I'm curious how much time the training takes, the learning.
Yeah.
And
thank you very much for the question. So first question was about the temporal difference method and the Monte Carlo methods, right? So what do we need for? So when you have a neural networks, we have built the architecture, but question is, how do we train it? Or in other words, how do we update the weights, biases, and etc. other parameters? So here, this is our gradient. Basically, we are going to update our parameters based on these equations. And as you can see, where these equations come from? These equations come from either this Monte Carlo methods, which is going to say that we are going to look at the total reward. Here is the total reward is given in our equation, or it's going to be dependent on this equation. Basically, it's on the temporal difference error. So this is well-established, well-known, and well-studied methods, and usually they determine how we take that gradient. On the question of the training, so this is a training for our 50 nodes case, I believe with 20 CPUs, and this is an easy instance. It took around 6 hours.
Okay.
Yeah.
All right. So in order to implement this online, you would have to maybe, train it during the night and then have a new solution, or maybe every 6 hours, right? If you want to implement this in a real world system, there would be a phase when it's learning, and then every 6 hours you change your solution. Is that correct?
So I think also the question is what is changing during this period of time. So if you have like pretty much the same network, transportation network structure, when you have like already established charging stations, already some like very close location of the same almost location of supply and demand nodes, you don't need to retrain it again and again. It's going to be the same thing, you just need to run the solution. But if there is a substantial change in the transportation network, and you wanted to make sure that it's actually fitting to that problem, you need to do retraining, and in that is going to depend, the training time is going to depend on the network size and charging levels, like the difficulty of the problem. Is there enough charging stations? Is there enough demand nodes? That kind of criteria.
All right, thank you.
Thank you.
Anybody else? So how far along are you in your PhD studies?
I think it's my 4th year. Yeah.
Okay, so you'll be finishing up maybe in the next year or so?
Yes.
Okay, excellent. Okay, well, it's a 12:40 now, so we've been going at it for about 40 minutes. If nobody else has any other questions, we'll say so long and see you next week. Okay, thanks so much, Aigerim.
Thank you very much. Bye-bye.
Bye.